From the preceding theorem in the previous video, we are going to continue. In particular, we know that any alternating multilinear function has the form of this equation for some constant c. If we then choose an n by n matrix A, the value of this multilinear function, where the ith element of our multilinear function phi is the ith column of the matrix A, and we let c equal 1, then that function evaluated on that matrix in that way is called the determinant of that matrix, and you denote it as determinant of A, such that the determinant of A, if we continue our proof, we know that this is equal to this. So we say that this is sum over all the entries j1 to jn equal from 1 to n of the sign of those permutations of the product of the elements diagonally multiplied together according to that permutation. This summation is formally extended over all choices of j1 to jn, with the understanding that j1 to jn is equal to 0 unless the indices are non-repeating. That is, we use j1 up to jn is equal to 1 to n, and then we just ignore the terms where there are repeats of ji's, because if those are repeats, then the sign term will cancel them out. From this, we can derive some basic properties of the determinant, namely those described by theorem 1.21, which is that the determinant mapping over field F satisfies the determinant of the identity is 1 for the identity matrix, the determinant of the transpose equals the determinant of the matrix, the determinant of a product is a product of determinants, and that the determinant is non-zero for non-singular matrices, and the converse is true. Let's prove these results. By definition, we have the determinant mapping normalized such that the determinant of I is equal to phi of delta 1 up to delta n, and we're going to have that be 1 because we said that our constant c was equal to 1. And then we use the other properties to derive that if we consider just the n basis vectors, that has to equal 1. Refer to the previous video to rederive that fact. For number 2, when we consider the transpose matrix, we know that the products of A1J1 up to ANJN and the reversed order AJ11 up to AJNN run over the same set of values as the indices run through all the permutations of the integers 1 to n. So the basic formula 1.69 has the same values when the terms aij are replaced by aji. So therefore, it's just summing the terms in a different order. Therefore, the sum is still the same. If we have matrix A being aij and B being bij, then consider the jth column vj of their product ab, which we know to be the sum over some indices from 1 to n of aik, bkj, and it's the linear combination vj is the sum of a vector times the coefficients bkj for a vector going from a1 up to an. Therefore, for any linear function phi from fn to f, it follows that phi of vj is equal to phi of this sum, and then we just apply the multilinearity of phi, the linearity of phi to pull out the bkj and put the phi through the sum, which gives the sum from 1 to n of bkj phi of ak. Note that the determinant defined previously, the determinant is defined by what we just talked about in the beginning. And since the function big phi is multilinear and alternating, the determinant of ab is equal to phi applied to each of those. And then we push this through, since phi is multilinear, of the sum over all permutations k1 to kn from 1 to n of these product terms times the phi of this original one. But if we can rewrite the phi of ak1 up to akn using our results in the last video to write as the sign of the permutation k1 up to kn of times phi applied to a1 to an. But we'll note that this is just the determinant of a times the determinant of b, since this term is going to be the determinant of b and this term was given to be the determinant of a. Finally, let's prove that non-singularity is the same as having non-zero determinant. Let's do this in both directions. So we'll note if a n by n matrix is non-singular, then there's a well-defined inverse, A inverse, for which A inverse is I, and then we simply apply the results of 1 and 3 to determine that A inverse is equal to determinant of A times A inverse is equal to determinant of I is equal to 1, and consequently the determinant of A is not equal to 0. and its inverse we get is equal to 1 over the determinant of A, or the determinant of its inverse is 1 over the determinant of A. Conversely, let's suppose we have an n by n matrix for the determinant is non-zero. Then if we apply our results from earlier, the equivalence theorem, there exist non-singular matrices S and T such that SAT is equal to B, where B is equal to IK 0, 0, 0. That is, we know that for all non-zero, we note that for any matrix we can find equivalent one, and this happens for some number k with k between 0 and n. However, since by the equivalence theorem we have S and T are non-singular matrices, the determinant of S and determinant of T are non-zero, and by what we've just proved, so because they're non-singular, then they have non-zero determinant by what we just proved. While since the determinant of A is non-zero, we then have determinant of B is non-zero in view of our previous result that the determinant operates over products. However, this can only be the case if k equals n, because if one of the columns of B was all 0, then determinant of B is equal to 0. Therefore, B is the identity matrix of this size, and if k, then we have A as a product of non-singular matrices, so it is non-singular. That is, we've shown that SAT is equal to B, where B is the identity matrix of the appropriate size. Therefore, A, if you invert S and T because they're non-singular, you can invert them, gives you that A is equal to S inverse B T inverse. And since we know that non-singular matrices form a group under multiplication, we see that A is non-singular. This suffices for the proof. Next time we'll continue by considering some further properties of determinants. Thank you.